Another example where more adaptation of GCMs and a very specified use of GCMs has been brought into notice is the neurochemical analysis of amino acids. And in many cases derivatizations are carried out because the compound per se is not really a suitable material to be detected by GCMS alone. And so, I have taken this particular analysis or example of the analysis of amino acids by quantification of its derivatives, that is the tertiary BDMS derivative using ammonia and CI mode. We have seen so far that examples of EI methods were taken into consideration. So, where all are EI methods used? EI methods are used in most of the known compounds, unknown compounds, simple compounds, but under very special conditions where very small quantity has to be analyzed, or if the analyte is not sensitive enough to generate molecular ion peak, the CI method must be used. And this is one such example where I have brought to your notice that even derivatization is a very crucial step in order to carry out specific GCMS analysis. The GCMS quantitation for a large number of neurochemicals utilizing a single derivatization step is not a very common method, but it provides us by a reagent called N-tertiary butyl dimethyl N-methyl trifluoroacetamide, that is MTBS-TFA. Previous workers have utilized this derivative for GCMS analysis of amino acids, carboxylic acids and urea with electron impact and with positive chemical ionization using methane as the reagent gas. However, these conditions yield significant fragmentation, decreasing sensitivity and in some cases reducing specificity for quantitation with selected ion monitoring, that is the SIM method, using isotopic dilution combined with ammonia as the reagent gas for PCI analysis results in high precision and sensitivity in analyzing complex neurochemical mixes. In the case of ammonia as the reagent gas, all amino acids, polyamines and urea yielded strong MH plus ion with little or no fragmentation. In the case of carboxylic acid, M plus 18 plus ions predominated, but MH plus ions were also noted. The advantage of this derivatization method includes that it is a simple sample preparation method, a single derivatization step is required, and thirdly, direct GCMS analysis of the reaction mixture can be carried out. And fourthly, it has very high precision as result of isotopic dilution analysis. And finally, and fifthly, it is high sensitivity and specificity as a result of the strong MH ions with ammonia reagent gas. So, one sees that there is no hydrolysis of glutamine to glutamate or no asparagine to aspartate, and it is applicable to a wide range of neurochemicals. So, when it comes to analysis of neurochemicals, this particular method was developed precisely to get correct information about the sequencing of amino acids, and so this tertiary BDMS derivatization was a very typical case in the case of amino acid analysis by GCMS. Similarly, another method that I have selected where an MS and GCMS approach for rapid screening and quantitative determination of perchloroethylene in air has been shown. A new mass spectrometry, gas chromatography mass spectrometry. Now, you see MS and GCMS have been hyphenated or connected. When we write it with this slash sign, it means that two machines have been combined. Approach has been developed for the screening and quantitative determination of perchloroethylene, that is PERC, in workplace outdoor air samples, which could be extended to the screening of analysis of other analytes and other samples also. It is not that only this compound can be screened and others cannot be screened by this method, but largely it has been developed for the screening of perchloroethylene, that is, in abbreviation it is known as PERC, and whether it is a workplace or an outdoor air, these samples can be collected and analyzed by this method. This approach may be rapidly modified in order to be used directly as an MS detector for screening purposes, or alternatively as a common GCMS method for just confirmation of the presence of this compound called the perchloroethylene. The screening alternative by MS is approximately 20 times faster than the quantitative confirmatory determination of the GCMS method. Detection limits of both alternatives are sufficiently low to screen and determine the perchloroethylene compound in the above mentioned matrices. The advantage of this approach over other method is that in the present case the sample passes through the gas chromatographic column only when the confirmatory GCMS is used. For the MS screening method, the chromatographic column is bypassed by using an appropriate selection valve. In this way, the column lifetime is extended and screening time is considerably shortened. Again, there is a comparative method whether a direct MS could be used for this perchloroethylene compound or whether a GCMS method should be used for the analysis of this particular compound, which is very crucial in either indoor air or outdoor air, and the analysis must give confirmatory results, and it was found that both the methods are equivalent and are comparable, and one can carry out by either of them. Similarly, when very rapid determination of essential compounds in Artemisia saligenesis by GCMS had to be carried out, microwave distillation and simultaneous solid phase microwave extraction was carried out. Now, you will see that in the previous lectures when I was talking about different methods of extraction, we had taken into consideration and we had learnt about the SPME method. So, without going into the details of the methodology of SPME, I would now just directly refer to this method and why and how it was used in this particular essential oil determination. Two solvent free sample preparation techniques of the microwave distillation, that is the MD, and the solid phase microwave extraction SPME were combined and developed for determination of essential oil compounds in Artemisia. Using the method, isolation, extraction and concentration of essential oil compounds can be carried out in just one single step. To demonstrate its feasibility, the MD SPME was compared with the conventional technique. Why is it superior to the conventional technique? unless and until, as I told earlier also, we make a comparative data whether conventional is better method or whether this MD SPME method is better, we will not be able to conclude which is superior. So, one needs to make this comparative data and to see which method is more applicable in the determination of essential oil in artemisia. To demonstrate its feasibility, the MD SPME was compared with conventional technique. Steam distillation for GCMS analysis of essential oil compounds in artemisia was carried out. 49 compounds were separated, identified by the present method, while only 26 compounds were detected by the SD method. That is, the steam distillation method could only be able to recover 26 compounds, whereas the new method, that is the microwave distillation followed by solid phase microwave extraction, gave 49 compounds. So, obviously, the number of components that came out of simple steam distillation was much higher as compared to the number of compounds which were yielded by the MD SPME method. And so, the SD method required long time, 6 hours to isolate the essential oil. Large amount of organic solvent was required because it is a steam distillation process, it takes longer time, more solvent for further and further extraction, and even then it was able to give only 26 compounds detailing, and whereas the other method gave us the detailing of 49 components. Therefore, the MD SPME needed only very little time, 3 minutes were required to extract, and the sample preparation method was also not very difficult. No organic solvent was used, and so in all these parameters MD SPME method is much superior extraction method for essential oils of artemisia as compared to the conventional method and the steam distillation method. The results show that MD SPME, when connected to GCMS, is a simple, rapid and solvent free method for determination of essential oils. So, where you have seen that how from one method to another method we are trying to progress and learn more and more intricacies of using the GCMS and modifying the GCMS either from the extraction point of view or from the analysis point of view, where we are changing the EI or the CI mode. Development of headspace. SPME, when it is coupled with GCMS, this is a very typical method for the analysis of terpenoids in wines. It is important to be able to know the exact quantitative description of wines in terms of its terpenoid content, and that is why a dynamic headspace solid phase microwave extraction methodology was developed for analysis of varietal aroma compounds, and it is a must in the case of wines, because a spirit wine with an ethanolic content of 18% volume by volume must have an edge over the terpenoid analysis. The factors which influence in the headspace solid phase micro extraction efficiency are the fiber coating, extraction time and temperature, pH, ionic strength, ethanolic content, desorption time and temperature. These parameters were all optimized. You see, there are so many parameters. What is the fiber coating? What is the extraction time that is required? What is the temperature at which it is to be done? what is the pH of the wine at which this should be carried out, what is the ionic strength of the wine, and how much is the ethanolic content, how much time does it take to dissolve, so, and at what temperature the desorption takes place, then only this method could be effectively used with GCMS. The best results were obtained for a 85 micro polyacrylate fiber with a 60 minutes headspace for must and a 120 minute for wine samples in a 2.4 ml sample at 40 degrees with 30% sodium chloride. The extract is injected in the splitless mode in the GCMS variant system and was separated on the Stabilivax capillary column. These are the details of the machine on which the analysis was carried out, and Stabilivax is the name of that particular capillary column. The linear dynamic range of the method covers the normal range of occurrence of analytes in wine with typical R2 between 0.98 and 0.99 for mus and between 0.98 for alpha terpineol and linalool. So, you can see that for most of these samples the range was that it had 2.5% of citronellol to 14.4% of nerolidol and so on, and therefore, one could find out whether this wine sample has enough terpenoids to be able to be used as good wines. Limits of detection obtained are in low range, that is from microgram per gram range for all compounds that are analyzed. Another very typical case that I have selected where GCMS has been used extensively, and that method is in tube silylation with thermal desorption in the GCMS machine for the determination of hydroxy PAH in water. Now, what are PAH? PAH are polyhydrocarbons, polycyclic aromatic hydrocarbons. Now, they are very notorious compounds because they are persistent organic pollutants. For the determination of hydroxy polycyclic aromatic hydrocarbons, that is OH-PAH, a simple and sensitive method based on the silylation of OH part of the PAH using NO-bis trimethyl silyl trifluoroacetamide BSTFA in combination with thermal desorption at the GCMS was carried out. This method was performed by way of direct silylation in a TD unit, that is in tube silylation is carried out coupled with a GC inlet. So, everything is being done in a very compact and inserted manner. There is no big reaction flask which are attached to the GC inlet. There is a small tube and there the silylation reaction is carried out, and that is connected because all the silyl compounds are very volatile. So, they come into the GC inlet very readily. Both a good detection limit, that is 4.1 picogram per liter sensitivity and very high precision was observed and achieved, and almost 21 such hydroxy polycyclic aromatic hydrocarbons were studied using a full scan mode, that is the M by Z from 40 to 550 AMU was covered by this particular machine organization. Although recoveries of 21 hydroxy PAH from the spiked 3% sodium chloride solution ranged between 9 to 304%, those of 11 hydroxy PAH fell between 70 to 130%. Thus, the present method was applied to a seawater sample collected from an industrial port and 9 OH PAH including 1 and 2 OH fluorininone and 1,8 and 2,6 hydroxy anthraquinone were determined at concentrations as low as 0.49 to 5.8 nanogram per liter. So, you can see that how precise is this silylation method and how accurately the hydroxy polycyclic aromatic hydrocarbons can be analyzed through this specialized technique of GCMs. Aromatization of organic matter induced by the presence of clays during the pyrolysis GCMs. Now, I am giving you the varieties of GCMs and its adaptation for different samples, so that you are aware of the fact that so many variations can be carried out by this particular method, which is broadly called the gas chromatography mass detector. The macromolecule characterization of fossils or recent organic matters in soils and sediment is frequently carried out using flash pyrolysis, gas chromatography, mass spectrometry, that is PY-GCMs. Such analysis provide information on the organic matter, structure and reactivity, and can be applied on isolated organic materials or on raw samples. Nevertheless, working on pure organic material implies heavy and time consuming pre-treatments such as humic substance isolation, mineral removal by acids, which can induce molecular alteration of the initial organic matter. Now, if all these procedures have to be carried out simultaneously, it is bound to make differences in the original material, and to be able to avoid this new method of pyrolysis GCMs was introduced. On the contrary, the PY-GCMs analysis on the raw sample, it avoids heavy preparation time and difficult preparation. The aim here is to test the clay influences during the flash pyrolysis of pure organic compounds, which can be generated during pyrolysis of natural macromolecules and humic acid. Moreover, flash pyrolysis was carried out with and without a methylation derivative, so as to evaluate its ability to limit clay effects. Now, one can see that these methods that are actually devised are very specific, and they have been carried out or they have been devised for a specific reason and for a specific compound, but this does not limit its use for only that compound. Although it was initially designed for that particular compound, but it can be used for similar types of compounds from time onwards. So, methods that are developed from time to time are generally focused methods, very specific methods, but these methods can now be a kind of an array of analysis methods, which could be also used for similar compounds, and that is how research goes on. Because when the GC machine was first devised, nobody had any clue about any kind of machine that would come from time with the passage of time, the GCMS machine, but there was a necessity which arose to find the new compounds, and therefore, a mass detector was attached instead of another detector like ECD or FID detector. and it gave more information about the analyte. So, similarly, these advances in technology and in methodology are brought about for the ease of the analyst. Another example that I have chosen is the forensic analysis of acrylic fiber by pyrolysis gas chromatography and mass spectrometry. Pyrolysis gas chromatography mass spectrometry is not only used as what I showed in the clay samples, but it is also a suitable technique for the differentiation of colorless polyacrylonitrile based fibers with similar morphology. Quite frequently, a comparison between items of this type is necessary to assess the reliability of the reconstruction of a crime. Now, when we look at the forensic analysis, it has to be related to some kind of crime where some sample has been procured, and analysis of this particular forensic sample can give some clue to how the crime has taken place. But I will not go into the detail of that part, but we will concentrate on the chemical analysis. The comparison of hydrocyanic acid, acetonitrile, acrylonitrile, acetic acid, methaacrylonitrile, 1,3-dicyanopropene, 1,3-dicyanobutene, 2,4-dicyanobutene and 1,3,5-tricyanohexane were the degradation products deemed most useful for discrimination of the samples. Now, when we have samples of acrylic fibers and pyrolytic gas chromatographic analysis is carried out, these are the compounds like hydrocyanide HCN or CH3CN, acrylonitrile, acetic acid. These are various components that would be deriving from a big macromolecule of acrylonitrile fiber, and if these are present, that means it is a clue that it is an acrylonitrile fiber and that these components have come out of degradation. Principal component analysis was employed for pattern recognition. Although fibers are industrial products very similar in structure and properties, the concentration and the distribution of head to head arrangements of the monomers differ slightly. Now, when we have a macromolecule, it always is not that all the monomers are aligned in one particular manner. There could be some alteration in the arrangement of different monomers, and that is what we get idea from the pyrolytic gas chromatography mass detector. These structural defects alter in a significant way and the composition of the mixture of pyrolysis products. This allows for the differentiation of fibers, which are often important traces in criminal investigation. So, depending on whether the sample was from the same origin or was from different origin, and whether the monomers have a different pattern or the same pattern, gives a lot of clue, and that is why it is used in forensic analysis. So, you see the versatility of GCMS machine, be it clay, be it forensic samples, be it wine samples, be it terpenoid analysis, various modifications and various adaptations help us to use this particular universal machine for different types of samples and gives us very sensitive and very accurate results to be able to interpret the required information. So, with this we have come to an end of a very important detection machine, which is called GCMS. I would now like to draw your attention to the fact that GCMS machine, let us now just recapture what we have learned in this lecture, how is the GC machine connected to the MS, why is this detector more sensitive, what are the different types of compounds that can be analyzed, and what are the different types of adaptations in extractions which need to be taken care in terms of doing a very specific GCMS analysis. So, if we go one by one, GCMS is a machine which is a higher and more sensitive machine than the GC with a FID or ECD detector. This we have seen by making comparative data that the sensitivity results of GCMS is far more higher than the GC simple with an ECD or FID detector. Now, mass detector, where it joins the GC machine, is called the interface, and the mass detector is the most sensitive part of this machine. The GC part remains as common, whether it is a GC with a FID or ECD detector or a GC with the MS detector, the GC part remains the same. There is an inlet, there is a column, there is an oven, and the compound is made to go through this column with the help of a carrier gas, so that there is proper separation on the column. That part remains the same. Once the compounds that are separated on the column enter the mass detector, that point is called the interface. And when it enters the mass detector, there are three discrete regions in the mass detector. One is the analyzer, the first part is the ionizer, second is the analyzer, and the third part is the detector. That means the separated compound, when it enters the ionizer, there is a beam of electron of 70 electrovolt which is continuously bombarding the compound, and because of this the molecular ion peak is generated, and when the molecule is then further on bombarded, the daughter nuclei or the daughter ions are formed, and this fragmentation pattern for a compound is always the same. It will not choose to break from anywhere and everywhere according to this electron impact method. However, in some cases, as what I mentioned, that electron impact may not give the molecular ion peak, there it is necessary to have another alternated mode, and that is called chemical ionization method, where methane gas or ammonia gas are used, and then molecular ion peak can be traced. But the CI method is less sensitive method as what I mentioned, and so it is just a supplementary or a complementary method. However, we should mostly follow the EI method. Now, after the ions are formed, the ions are made to move towards the detector, and by the sizes, the smallers will reach first, then medium sized ion will reach, and then the larger ions will reach the detector, and then this detector then amplifies the signals and gives us the spectrum of the compound. Now, when we go backward, that is molecular ion peak is the standpoint. From there we move on and see how the fragments had broken. That gives us an idea about the molecular structure of the compound, and depending on different types of compounds that need to be analyzed by the GC machine, their extraction methods need to be varied, so that most and more compound can be extracted. The better the extraction, the better would be the analytical result. And so, it always must be chosen that the extraction method must go hand in hand with the analytical tool that we are using. Just the way we cannot use very readily packed columns of the GC in a GCMS machine, only capillary columns are recommended. Similarly, we need to make certain adaptations when we are analyzing compounds on GCMS. So, these were certain points that I thought would be of reference, so that you know what GCMS machine looks like and works like.